FB will be equal to MB I Y star A star shaded. Because here I pick this block, I cut it horizontally. So that means the shaded area on this side will be equal to on that side. Are we okay? Yes.
Shouldn't the force be negative?
Yes, here I focus on is the magnitude. Here, the total horizontal force. Okay, here is the magnitude. The magnitude. Let me fix the magnitude first and then go to the slide second. Okay, the magnitude of this one, the same thing, the magnitude. And now I'm going to fix the directions. You can see this is the integration of the stress. So you can see the stress is pointing at the B section here. At this side, the section, the force go to that direction, right? So that means this is the direction of the FB. The FB will be going to that direction. Let me use the different hours. Again, right now we have the magnitude, and I want to determine the direction. What is the direction? So the total force acting on the shaded area will be pointing to this direction. This is the FB. Direction of FB with such a magnitude. And how about the total force at A? Which direction? Integration of FA. That is the total force FA is due to the integration of the stress. Which direction? Go that way. Okay. So again, right now we're doing is this. This beam is climb. We have a point loading. So that means the bending is different from place to place. And I simply want to find out what is the balance of what is the force on this side and on this side in the horizontal direction. And now we have this magnitude. We have the directions. My follow-up question asking you is, would FA in magnitude equal to FB? Here we have a magnitude. Maybe I can get one more step further. What is MA? The magnitude of MA is this one. The magnitude of MA, so that is PXA divided by I, Y bar, A star, shaded. And again, the magnitude of MB equal to this one, PXB divided by I, Y bar star, A star shaded. So one more step analysis. These are the magnitude for the force here, not the magnitude here. Which one? Are they equal in magnitude? No. Which one is bigger? This one is bigger. You can see I just draw it a little bit longer, so that indicates this force is larger than this one. Okay, now we're back to our original scenario. This is not the pure bending anymore, but this is the bending that has the bending distributed different from place to place. For this scenario, right now you can see the bending on this side is smaller, this side is larger, which means the bending on this side induces less bending stress. This bending stress is larger. Equivalently, the bending stress induces the normal force on this side larger, on this side smaller. Everything must be in equilibrium. So what happens? We must have another thing to get a balance. So I think I draw in the different directions. But anyhow, at the bottom side here, we must exist this other reaction to get everything in balance, right? Okay? And that is reaction force. And my direction here I draw is indirect, but you know this should have the reaction. So that means to get in balance, we expect at the bottom side, they exist delta H. For this case, delta H FA plus equal to FB in magnitude. So this is due to the force in x direction equal to 0. So far so good? So this is a very straightforward analysis, and this is exactly the lecture our textbook talk about in I think 3 pages. I just mentioned asking to preview last night. They exactly talk about the process here. Okay, and again, it's in a being not due to the pure bending, we expect in each level they must have the reaction. However, in pure bending, that means the bending stress on the two sides will be equal. That means FB will be equal to FA. So in pure bending, do we expect delta H? That should be 0. So for pure bending, we don't see this kind of strength, the reaction force. Okay. Now you can see, right now I've cut it. So that means I destruct the bonding integrity. So right now you can see once I bend it, you can see, oops, that one, they basically the material debonded from each other, like this. Okay, so that is the debonding. Debonding, that is due to the existence. Here I couldn't provide the force to overcome such a delta H. Almost there. So right now that's the delta H, and you realize that delta H is a reaction exists underneath. So that is a force parallel to this cross section, right? So are we able to calculate the average shear stress over this cross section? How much? Delta H divided by the area of this one, and then we can do the calculations. So let me turn this off. Again, everything I'm talking about is in our textbook. So if you wouldn't follow up my talking, you try to comprehend by concept, and then you go back to the textbook, you will see the detailed formulation. Okay, so the point here is try to grab the concept. So right now I'm going to calculate the average stress onto the bottom side here. Okay, so the tau averaging induced by delta H at the bottom area. Okay, hopefully you know what I mean. The bottom is this one here. Okay, equal to tau average will be equal to, by concept, definition is force divided by area of the bottom. Okay, then we plug into the magnitude. The delta H is how much? Delta H equal to FB minus FA divided by the area. The area, for example, here, let me say my beam here has the thickness T. Okay, so this side is T. So let me label this side. Is T. Okay, and then this side is how much is xb minus xa. So that one is picking up from the distance here, right? So for this one, we have the distance, the length here from here to here is xb minus xa. Are we okay? The xb is the coordinate of this, and xa is the coordinate of this point. Okay, and then this dimension, let me call t. So here the area will be equal to xb minus xa times t. Okay, we further do the calculation. So we simply plug in fb equal to p xb times y bar star times a shaded, and fa equal to p xa y star a star shaded, and then divide by xb minus xa times t. And oh, I forgot. Here divide by I. Sorry, p over I. Here is p over I. Well, so far so good. Okay, and again, what we are doing is we're looking for what is the average stress here in the horizontal direction here. Okay, so now we simplify this. So here let me try to get the things out. So those are the constant. So let me turn those constant out of the calculation. So that will be p over I y star a star shaded, and times xb minus xa divided by xb minus xa times t. So eventually this is p and in our formula, in our textbook, basically in most of the textbook, we define this term. This term, what is the y bar star? Again, the y bar star representing is the centroid of these selected cross sections to the neutral axis. Okay, and a star, that means the area of this site. So basically the star representing is our selection. So right now, today, I select a such shallow piece. You can select even the deeper piece up to your interest. Okay, and that is about the design problems. So for this one, for those kind of the selection, we simply define this term. We define as a cube, and let me give you a term of what is a cube. I forgot the definition. What's a cube? There's a long name that's called the first moment of, the first moment of the selected shaded area. In the cross section. Basically, that is called the first moment of something. Okay. So here, very clearly, the tau average equal to PQ over IT. And what is P? P is our magnitude, and P is here, the magnitude is here. And for this case, the P is constant. Okay, but for other scenario from your learning, when we draw the shear diagram, the P doesn't have to be constant. But for this simple case, I pick it as a constant. So basically, P representing, let me extend the general concept. In general, tau average equal to VQ over IT. Here I replace P by V, try to indicate P is actually representing the shear force, or we call the transverse loading on that position. Okay, and again the V, basically here is the V and that's the V. So here the V is, let me give you the definition here. So here the V is the shear or transverse loading. Shear force at here and the cross section. Okay, so right now we pick is two cross sections, 1 and 2. Okay, so let me use at the selected cross sections. And Q is the first moment of inertia of the shaded area. And I, again, I'm going to ask you, what is I? I just asked you a few minutes ago. What is I? I is the moment of inertia of entire cross section, okay, about the neutral axis. And A, the T. What is T? T is the thickness of the section. And I can tell you, this is the only equation in this chapter. And all the applications, all the calculations are derived from this single equation. And from this single equation, so that's what I mean, a little bit challenging, because you can see for this equation actually involve a lot of the different concepts. Okay? So when you go back to review the contents of the textbook lecture notes, try to rewind your visualization of this model, okay, and know where it's to where. So this is the magnitude of the shear stress. I think I should have done that. Okay, so now again, let us review the whole concept one more time. And this is a cantilever beam, and come here, we have point loading. So point loading bend over to here, then always smaller bending on this side, larger bending this side. Correspondingly, we have induced the normal force, larger FB, larger on this side, smaller normal force here on this side. So that will causing equivalent the horizontal reaction here, right? Are we okay?